Okay, so today we're going to be going over rational roots theorem. And as you can see from the board, there's a lot of work that we're going to be going over, so you're going to have to hold on tight for this one. Okay, first we're going to start with f of x right here. This is just going to be our standard polynomial. And I'm just using these coefficients of a, n minus 1, a1, and a0. And these are integer functions. It's really important. Rational roots theorem will only possibly work if these are all integer coefficients. Okay? It's only going to possibly work if these are integer coefficients. Now by possibly, I mean sometimes the roots are complex or irrational. So it's not going to work for every single polynomial. But it will work for the rational ones. We're going to talk about that more later. Okay, so that's our polynomial. P and Q, which we're going to use to input into our f of x function, are coprime integers. And basically what that means is that they have a common factor of 1 between them and nothing else. For example, you can use 14 and 15. Those two numbers are coprime. Now, 14 is not prime, 15 is not prime, but together they do not have a common factor besides 1. Now, if you took 14 and 21, those would not be coprime because they have a common factor of 7. Okay? Hopefully that makes sense. If not, make sure you ask. So P and Q are coprime integers, and the coefficients are all integers as well for this. So what I did for this first one is I inputted for x, P over Q. So as you can see right here, I just replaced this x with P over Q in the function. Next, what I did is I multiplied each of these terms by q to the n power. Okay? So I have an times p over q to the n power, and I just multiplied that by q to the n power, and it canceled out the q to the n. As you can see, it just says an p to the n. Okay? I did that to all the remaining terms afterwards, and as you can see, this constant now has a times q to the n power in it. So that's this whole line right here. Okay? From there, I subtracted off this a0 q to the n from both sides, and so it ends up on the other side right over here. As you can see, it says negative a0 q to the n power. So it's no longer on the left side of the equation. Okay? Next thing I did is I factored out the p. So I factored out p here from this entire side, from the left side. And remember, I moved this to the other side, so we don't need to worry about that anymore. So factored out the p right here, and I have an p to the n minus 1, and I factored out from all the other terms as well. You can check my math on that if you want. So that's where I'm at right there. Factored out the p. Now, because p and q are coprime, and p is factored out here, p must be a factor of both sides. Okay, and this is kind of hard to understand, so I'm going to kind of explain it here. I'm going to kind of break it down. Okay, this whole thing right here has to be an integer. Okay, q is an integer, an minus 1, and everything in between are all integers as well, because I said it right here, integer coefficients. So all of these coefficients are integers. So this whole thing in the parentheses right here is an integer. P is also an integer, because I said it right here, P and Q are coprime integers. Okay, these both are integers as well. Okay, and since P and Q are coprime, basically I'm just reading right here, P must be a factor of a0. Okay, if I divide both sides by P, I'm going to end up with negative a0 q to the n divided by P. This has to be an integer on this side. It has to be a factor, because this whole thing right here is an integer. So this has to be a factor of a0. And that's really, really, really important to know for rational roots theorem. If that wasn't the case, this wouldn't work. Okay? So far we've proven that p must be a factor of a0. It has to divide evenly. It will not divide evenly to q to the n because it's coprime. P and q are coprime. It will not divide evenly into q. Therefore, it has to divide evenly into a0, because this right here is an integer. Okay? Really important. If you don't understand that, please ask. Okay? So that proves that p must be a factor of a0 for rational roots theorem. Okay, what we're going to do on this side now is show that q must be a factor of an. And I wrote a0 here. That's a little error. Let me fix that. an. Okay, and I'm going to prove that right now. So here we go. All I'm doing is taking the line from right here, taking this line, and all I'm doing is taking this an p to the n power, and I'm subtracting it to the other side. So as you can see right here, it says negative an times p to the n power. So that's all I did is subtract off this an p to the n. Put it on the other side, okay? And I kept this a0 q to the n on that side. So basically I did the same thing I did here, only instead I moved the an p to the n instead of the a0 q to the n. I know this is getting tricky, but you can watch this multiple times. Okay, from there I factored out the q, just like I factored out the p before. So I end up with this long integer, basically, and I forgot a little plus sign here. Fix that real quick. And you end up with, factoring out the q, and you end up with the negative an times p to the n power from what we had before. And q must be a factor of both sides, because as you can see, q is multiplied here times this integer. And because p and q are coprime, it must be a factor of an for the same reason that p is a factor of a0. The exact same reason. This whole thing is an integer right here. So if I divide by q, if I divide both sides by q here, I'll have negative an times p to the n divided by q. That has to be an integer based on the fact that this whole thing is an integer right there. So in order for it to be an integer, it would have to divide evenly, this would have to divide evenly by q. And since p and q don't divide evenly, that means the an has to divide evenly. If an divides evenly, then it's a factor. Q would be a factor of an. Now, based on this, we can actually use this to find the roots, the possible roots, for our polynomials. And that's going to be the next video. I'm going to show you some examples where we can actually use this. So if you didn't understand anything, and you want to understand something a little bit more, please ask in class. Let me know.